All right.
So as always, thanks for joining us. Today's webinar is being recorded. It will be uploaded to our YouTube channel where you can find by searching Spear on YouTube, or you can go to our website at eepartnership.org. And under the news section, you'll find the resource page. And under the resource page, you'll see a link to our channel. Within about 72 hours of today's presentation, you'll receive a course evaluation survey email from Kathy Lawrence. Please complete this survey and send it back to her to receive your course completion certificate, which will contain the course ID number that you'll need when reporting your CEUs to ICC. Lastly, the chat feature is open, so please use it to report any technical difficulties you might be having during this presentation. And then the Q&A feature is open as well. I will take questions as they come. And then when Alex has a brief pause, we're going to ask some questions as they come through. Or Alex, do you want me to hold them to the end?
No, as we go is fine.
Okay, perfect. So we will, as they come through, we will go through those. So without that, for some reason, there you go. Without that further being said, then we can just go ahead and get started. I know you have a lot of information, so I'll stop sharing my screen and you can take over. Hold on one second.
Oh, okay.
All right.
And let's see. That's my share. Okay. And cool. Can we see the title slide making sense of the mess here?
Looks good.
All right. Awesome. All right. Let me move this toolbar somewhere useful. There we go. Thanks for coming. My name is Alex Meany. I am the owner of Mean HVAC Consulting. I was the head trainer for RightSoft for about 20 years. I'm a contributing author to the new edition of the Manual S, the Manual D, having some preliminary talks with the folks over at ACA on participating in the new Manual J. So I know my way around the HVAC design process pretty well, you could say. And so we're going to go through, I'm using RightSoft reports for everything that we're going to go through, but I want to make this as sort of general as possible because there are quite a few products that are certified for HVAC design use by the ACCA, and trying to go through every single one of the products would have been, I think, a little confusing. So we're going to focus on the core issues. If you, as we already said, if you have questions, feel free to fire away as we go. This was put together in about a week, so it's not super duper like it has to be in this exact order and structure. So, but try to keep them on the topic that's maybe on the slide at hand. If you miss your window, we can circle back to anything we need to at the end. Speaking of the end, I think we're probably going to devolve into a conversation about equipment at the very end. So I'm leaving that stuff for the end because I think it will spiral into its own topic. So we'll start with load stuff. Might as well start with the easy stuff, right? That's the easiest way to go. The first thing that most planner viewers are checking is the square footage of the building. And that's a nice, easy one. Everybody knows it. I'm not telling anybody anything they don't know. There can be some snags when checking square footage. First of all, square footage technically isn't very important at all. Heat only transfers through the square footage at the lowest floor, at the bottom floor and above the garage in Texas. And if you're on a slab and we're talking cooling load, it doesn't even do that. There's literally no heat transfer there. If there's any heat transfer, it's going the wrong direction or the right direction, actually. So it's a net cooling effect. There is no cooling load on the floor. That's why it's a terrible tool for sizing a system, right? How many square feet per ton? Because it has very little to do with the load. But when you are trying to check somebody's work without redoing it, it is a very good place to start. I have seen too many people focus very laser-like on square footage and make it like the main pass or fail of the process. And where that can get a little messed up is open areas. In some cases, you may need to treat the upstairs area of a great room and the downstairs area of a great room or foyer or whatever as separate spaces. If you are going to introduce supply air to the middle of the space and the top of the space or the top and the bottom, if you're going to do it at 2 levels, you need 2 rooms to do that. And so it's going to count square footage of that room that you've added without, and that will cause a discrepancy between the builder's plan square footage and the printed square footage. It's a very common sticking point for the submittal process. So sometimes those things can be explained by that. And it's a simple enough thing to find if they print you the J1, which is one of the recommended printouts for from the ACCA. Their inspector liaison or plan review liaison people specifically designed that J1 form for looking over. And you could just find that there's, the room is counted twice and confirm that. I have seen, I've seen more than you would think. Architects and builders not updating the square footage block on their plan when making changes or adding options to a building. So it is something to be aware of, just to sort of maybe be able to zoom out a bit and make sure that that's not the case. The biggest thing or the biggest issue from the contractor side, who is usually who I'm working with, right? The vast majority, matter of fact, almost the entirety of my customer base is HVAC contractors. So I'm coming at this from sort of that end. They often get stuck on not matching the square footage of the plan exactly. That's not a requirement. Straight up, like that's a made up thing. You do not have to match the square footage of the plan exactly. This is load calculations, right? We're not doing structural. Structural, I need to be pretty exact. In load calcs, especially for things that are surfaces that are well insulated, plus or minus a bit is not much. And so there is a section in the manual J on how to measure a building, and the lengths of the walls, meaning basically the floor plan of the building, can be measured to the nearest foot. And that's obviously going to create a little bit of noise in the signal. The heights can be rounded to the nearest half foot, although that's not usually a reporting problem because we're talking usually floor areas, the thing that people are checking. There is an acceptable surface area margin of error for the measurement of the floor plan, and it's plus or minus 5%. So if they're within 5% of the builder square footage, that's an automatic, or should be an automatic pass. And just because something is a little bit off of that doesn't necessarily mean they did anything wrong. I know it is the easiest thing to look at, but you'd be surprised at how little difference a couple hundred square feet of wall might make to a load. So it really doesn't amount to a whole lot of importance. Obviously, it needs to be in the ballpark, that plus or minus 5%, but ultra precision is definitely not necessary. And you're going to find this on lots of different reports, but the writes-off report that I always recommend people print for their plan reviewers is called the project summary. It's got a lot of high-level information, including the square footage, right? It's under the heating summary because it has a lot to do with infiltration, actually, and that's more of a heating concern than a cooling one in terms of total BTUs. For you guys in the coastal area, it's both heating and a cooling concern because it's also where the humidity comes from. Randy, are we from all across Texas? Is West Texas being represented here, just out of curiosity?
Yeah, normally we have people from
Okay.
West Texas.
All right, cool.
Area. Yeah.
Yeah.
Guadalupe raised his hand. Yeah, he's from Amarillo.
Cool. Yeah, so it's a little bit of a different animal out there. The humidity thing isn't, you might as well be on a different planet when you're going from Amarillo to Houston in terms of humidity. And so the cooling, then it becomes true. Cooling isn't really all that important for infiltration. But that's where my square footage would be. Again, it got to be the lowest hanging fruit of the entire process. It's just not something that needs to be micromanaged down to a gnat's rear end, as they say. The next easiest thing to check would be the location they selected. So location is going to determine a few things, actually. The most important would be the outdoor design temperatures. Okay. The heating dry bulb, the cooling dry bulb, and the cooling wet bulb. Those are going to determine, those are typically how they're expressed in, say, Manual J. Technically, tools could show you a cooling relative humidity or dew point or any of those moisture data points from the psychrometric chart, but Manual J typically uses wet bulb. There are two valid sources for this information. You can get it directly from Manual J. The problem for you guys on that front is it's not available electronically. So if you don't have a physical copy of the book, it's a little difficult to reference. The Manual J numbers are actually based on the Ashrae published data from 2013, and it's and it's rounded very weirdly. Hank Kratowski did not follow standard rounding rules when changing numbers to the nearest tenth of a decimal to a whole number. So it doesn't match the Ashrae information perfectly. The other source of usable, allowable data is Ashrae. So Ashrae publishes this data every 4 years. So the 2021 data is the most recent. I like to encourage people to use the most recent, but it's technically not a requirement in the standard. And that makes sense since the ACCA data is from 2013. And there are a few sources that you can use. So Randy, I'm going to send you an email with a couple of links so that you can disseminate that to the people in attendance. But my favorite tool for determining weather location is the interactive weather map that a group of engineers have created online. It's the Ashrae Meteo.info, and it's /v2.0. And again, I'll just email that out. It is a tool that lets you find on a map where you're located, and if you right click on the map, it will give you all of the Ashrae weather stations available. And you can choose the one that would best match your area climate wise, because it can be a little difficult to pinpoint what's the right one to use. Now, we do in the planner view world occasionally try to simplify things for our planner viewers, and I love that, but sometimes we lose important information in the process. I'm not a huge fan of DOE county by county documentation. It is what Energy Star uses, but there are situations, especially as I get near a coast or near a sharp change in elevation. When I'm in those two situations, I start getting worried about the county by county weather information. It is usually very good, right? It's it gives you a list of every county in every state and a set of design conditions, again from Ashrae 2013, actually, that you can use and verify. But counties can be quite large and can encompass some significant geographical oddities that can have an effect on design criteria. And so knowing your local area is super important. There is one more that I did not indicate here, and that is local code. City of Austin, I believe, has a variance for the temperature, the design temperature they use. I think the by the book number is 99 and they use 100. That's off the top of my head. Don't go writing that down. I would verify that. But that is occasionally the case at a municipal or a county level, that they'll pass a code, or a state level. That I don't think that's happened anywhere but California and Hawaii on a state level, because then I have to break it down for all the places in the state. But on a local level, they will sometimes codify a certain design temperature, and Manual J does allow for that. When those decisions are made, it's best to consult experts. The state of Connecticut tried to standardize this and enforce one design temperature across the entire state a couple of years back, and they used the state capital, New Haven, which is right on the ocean. And when you go, only about an hour's drive north of there to their most populous city in Hartford, the design temperature increased the delta T by over 50%. Huge difference in the numbers. And sometimes these things don't get thought all the way through. So do be careful with that, right? Oversimplification is almost never a good thing. The other factor is actually two other factors that the location can have an effect on is elevation. So my West Texas, this is why I asked about West Texas. The folks in West Texas, once you get above 2,500 feet above sea level, that's the magic number. That's where you start adjusting. You're always adjusting the load if you're using software. I don't care whose software it is. If it's Manual J certified, they're using psychrometric adjustments for infiltration, ventilation, things like that. So elevation does impact the load. It's not a huge impact, but it does. But it also impacts equipment performance, both cooling and heating. And so once you get above 2,500 feet above sea level, you want your load adjusted because it starts to really make a difference around that height. And you can use some manual S tables for derating the performance of heating and cooling systems. They get worse at altitude because they're not moving as much mass. Then there's one other factor. So if they had their temperatures right, but weirdly their location was way off, pretty weird scenario, but I've seen people just try to change, like national builders. Sometimes they'll try to update a design where they'll just change the outdoor temperatures to match properly. But if they're using a design for Indiana in Texas, which I saw once, it actually throws off the cooling load. The latitude that you're at actually has an effect on solar gain in the Manual J. That is a step in the process if you're doing it by hand. You actually have to look up a table that has solar heat per latitude or per latitude range. And the more southern you get, the higher that number becomes. So there is yet another little factor. And one last wrench in the works, if you will. You wouldn't perform a standard load calculation at these conditions, but if you wanted to use Manual J for sizing dehumidifiers, all right, if you're going to size a dehumidifier for the needs of the building to maintain 50% relative humidity, you can do a load calculation at what are called peak dehumidification conditions. Pretty much the only place you're going to get those. They're not built into any software program that I know of. You have to override things to get there. But this page here, this tool here that gives you access to the raw Ashrae data, they have what are called peak dehumidification conditions, which are like peak cooling conditions, but they are for the most humid day and not the hottest day. If you're sizing the dehu, not the air conditioner, the dehu, you can use those conditions in a load calculation to determine what the need is. Didn't even put it in my notes because it's so important and I just assumed I would remember. When using Ashrae data, there are different data sets. They break their numbers down by mean extreme, 0.4%, 1%, and 2% for cooling, and 99%, 99.6%, and mean extreme on heating. Those options are meant for commercial designers to be making choices there. In a residential design, you shouldn't have the choice. You're not supposed to have the choice. You're supposed to use 1% for cooling, 99% for heating. And the same is true for that peak dehu, 1%, for peak dehumidification is the standard. Some people advocate 2%. I mean, if they're going to go lower, that's fine. But 1% cooling data, 99% heating data, those are the requirements. So on the other half of that very important part of the load, and probably the most manipulated, I know I'm spending a little bit of sort of extra time on this than you might have wanted, but
No,
oh no, okay, good.
yeah, sorry, just before you go to this next one here. So would you recommend, in your expert opinion, would you recommend if someone's doing a foam house that they use this peak dehum calculations with manual J to plan for that, since humidity is a bigger issue with foam houses?
So humidity isn't, well, yeah, humidity is a bigger issue with foam houses because it has nowhere to go and tends to float up, and we tend not to have any moisture removal system at the top of the building, right? When we okay, yeah. One of the most fundamental things that is important to know that a lot of people don't, people think of humid air as heavy, right? Because it feels heavy. It's when you breathe it. The analogy we use, you know, like you can cut it with a knife, it's heavy. Humidity is light. Water vapor is lighter than air, and humidity will float up on its own naturally. Now, diffusion, aka vapor pressure, does keep things somewhat uniform, but somewhat, with a lot of emphasis. And so the problem you have in these homes, normally your air barrier, which functionally is sort of a vapor barrier, although maybe not intentionally, is normally the ceiling, and you're returning air from the ceiling or near the ceiling, right, in a room on the top floor. When you have an encapsulated attic, your air barrier is no longer the ceiling, it's the roof. And there are a lot of expensive codes that kick in if I'm going to condition my encapsulated attic, and so we tend not to. And so there's a path for humidity to rise to that location and nothing actively taking it out. And so it builds up. Also, open cell foam and wood are pretty good at absorbing moisture, so there's a place for it to go and get stuck, which is what causes all of these issues. I don't necessarily recommend sizing a dehumidifier for that application, even for the total latent load of the building. That's really not the issue. It's the location. So a dedicated dehumidifier that is pulling air from that attic space and removing humidity from it is the key. And in terms of how large it needs to be, it's probably not very, right? Because slightly higher humidity levels in the attic aren't going to create problems. It's when they get really high that it starts to have, physical issues. And literally anything to remove moisture. I mean, not literally anything, desiccant packets or things like that aren't going to work, but active dehumidification in the space would be pretty effective. Another reason for that is some of the sources of humidity in those places are like leaky connections at the bathroom fan when we take a shower, right? Or whatever it is that's letting that humidity in. It's not necessarily the load on the building. It's the fact that it's congregating in that one area. Now, if you're designing a ventilation system, a dehumidification system for the home, right, to maintain a comfort level inside the home, then yes, I would recommend using the peak dehu conditions, because the thing is going to be doing its job. The toughest job the dehumidifier has is not on a hot day. It's because on the hot day your air conditioner is running, and besides your air conditioner, right, it should take care of that load. There are situations where it doesn't. You might have to have supplemental, but typically that's the case. So what you're trying to do with a dehumidifier typically is deal with these part load conditions, which tend to be more humid and cooler. And so the most humid and cooler of the data points is that peak dehu. And I've done some work with somebody who's done a little bit of research on this, and she's not 100% definitive, but so far in every location she's done the research, Austin, Texas seems to take the cake. They're the winner on the biggest spread between their cooling day and their dehumidification day. both in temperature and in humidity level. So it would make a difference when sizing a dehumidifier, but that's for sizing for comfort, not for fighting off encapsulated attic problems. Encapsulated attic problems. I don't know what standard I would use, but it certainly doesn't have to be that aggressive. That's not what you're not trying to maintain 50% RH in that space. Okay. Any other questions on our location stuff?
Nope, that's it.
All right. The other half of that, which is where, well, there used to be more wiggle room than there is now, but there's still clearly some wiggle room here, is the indoor temperatures. Again, very easy to identify on a report. There are multiple standards out there. The first one probably doesn't apply in most of Texas, although I won't 100% rule it out. 68 degrees for heating is what's recommended by the National Radiant Consortium. When they say when you have radiant heat, you don't need to keep it as warm to be as comfortable, which is fairly well proven science. And so they recommend designing at 68 degrees. They don't do anything to the cooling. The ACCA's recommended design, they call them default design conditions. And they're very particular about language over there. So I believe that's important to note. It's not required like it is for cooling. It's default. And it's 70 degrees for heating, 75 degrees for cooling with a 50% target summer relative humidity. The National Energy Code will throw out 72 degrees just to be different. I don't know why, like it's very annoying. But they have a 72 degree for heating, 75 for cooling, 50% RH for some of their standards. 70 heating, 75 cooling, 50% relative humidity is certainly a solid standard to use for the vast majority of Texas. There is language in the Manual J that says code officials, what is it? With the permission of the authority having jurisdiction or some language similar to that, we can change our indoor design temperatures, but it has to go through you guys. That's your call. But there is clearly a little bit of wiggle room happening here. And it is sort of codified, this last one. It is a part of the high altitude Manual S design procedures. So if you're in West Texas and you're in the high dry parts of West Texas, where you don't have a latent load, you don't have a humidity load or dehumidification load, I should say. You might want to change your operating relative humidity to something in the 40 to 45 degree range, whatever, not degree, I'm sorry, percent. Wherever that standard is, where you no longer have or whatever that standard is, where you start to get a small latent load, a small dehumidification load, because that's going to be the number that when you let outside air in, it's drying out your house, not making it more humid until it gets to X point, right? When you find that, that should probably drive your assumptions about equipment performance. Equipment doesn't perform as well with dry air as it does with wet air. It reduces the capacity. And so a procedure in a document associated with the Manual S, I don't know if it's normative or not, but I certainly would strongly recommend that people follow it, would be in very dry climates to adjust your relative humidity so that you are near zero on your latent load from your outside air to predict the indoor relative humidity for the performance of your air conditioner. So that's the one variation on 70, 75 that you might see that I would green light if I were you, because it's an appropriate design criteria in very dry climates. 50% relative humidity, you'd need a humidifier to get to 50% relative humidity. So it's just reflecting the reality of the situation. And the authority having jurisdiction, that's a ACCA favorite abbreviation. You're probably familiar with it. That's you guys can allow deviation from these numbers. For what it's worth, when I'm teaching classes in humid climates, I strongly recommend that they never drop below 72 as a design standard, simply because there's a lot of manufacturers where they're and like places like Houston, I would tell them not to at all. But they're 70 to 72, I would never allow anything below 70. Below 70, I can't get any manufacturer data on the performance of the system. And I would question using 70 pretty much for reasons of standard comfort. Is the bottom of the comfort zone, near the bottom of the comfort zone. But 72 is the point where some manufacturers don't publish. So between 70 and 72, some manufacturers don't publish data there either. Some do. That's the sort of gray zone. But I think 72 is a reasonable cutoff for allowing things for different situations you might be in. Or your job may be to follow the code to the letter and not allow that. But ACCA gives you the wiggle room. You, not the design, not the contractor. Let's see. Oh, I think I duplicated that slide there. It's really simple. It's the design temperatures, right? And it gives me the TD, the temperature difference, right? So whether it's the outside temperature or the inside temperature, that is what's going to impact the load. And when you're evaluating differences, this is the mistake that Connecticut made. They looked at their design temps and they went, oh, it's only going from 84 to 88 degrees or whatever. No, it was 84 to 92. I don't know. Whatever that range was. They thought it was a small percentage because they were comparing the 90 or the 84 to the number of degrees they were changing. No. It's the delta, right? It's the delta T. That's your big number right there. And the target humidity for the indoor, and that's the moisture difference, is just the difference in the amount of moisture in the air. They measure that in grains. It's a weird measurement. I think I'll take a pass on that unless anybody's has any questions. All right, the next thing I would look for, this is the easy stuff, the low-hanging fruit. I'd look for internal gains, the people and appliances. The easiest way to find this would be on the J1 form, which every manufacturer or every software company prints out a version of. And by a version of, it's this form. It's just, some of the stuff around it might be slightly different formatted. It is a standardized form put together by the ACCA, which is a big reason I use it for this presentation. So the number of internal gains breaks down thusly. It should be the number of bedrooms plus one for occupant gain. I personally, for retrofit scenarios, would allow for more people if more people actually lived there. Right, it was a multi-family, not a multi-family home, but like a multi-generational. That's what they call it, a multi-generational home. But for whatever reason, we have more people living there, and they really do. That would be a good reason to adjust the design. The appliance loads. So this one has a very high custom appliance. I grabbed a load calculation from a customer, happened to be in Texas, that I was working with recently. And they were designing something where an IT person had a small business in their home. This is, by the way, totally accidental. I just realized that this thing has 4,000 BTUs of custom appliances. And this IT person has a lot of hardware that stays on all the time in this little closet, basically. And rather than giving it a dedicated system, they wanted to tie into the existing HVAC to try to do it. Or the new HVAC that was going in to try to do it. And I don't know if that's allowable by code or not, but those pieces of equipment, they don't shut off. They're always putting out heat, which in terms of how the manual J lays out how to do internal loads, that's a gimme. You can use that. But for intermittent stuff, they recommend, don't technically require, but they recommend the use of their basic scenarios. So 1200 is the simple old school scenario. I actually don't teach people to use that. 2000 to 2400 is the scenario one, they call it. It accounts for not just kitchen appliances, but some TVs and other electronic allowances for the home. And there's scenario two for situations where you have like double refrigerators, an extra freezer, things like that, and that runs around 3,400 BTUs. And so that's like my range. I'm looking for an appliance load somewhere between 1 in 3,000, or let's call it 3,500 BTUs for like a normal house. And if I have, again, a multi-generational home or something where, we have multiple places where things are always going to be going, there are allowances for that. Other software programs, specifically Elite, they give you access to the broken down tables of individual appliances. Those are meant to have a run fraction associated with them. And some users will just spam the ever living heck out of all the appliances. And before you know it, you've got 10,000 BTUs of appliance load. That's a pretty big no-no. It can be an honest mistake. It's, people counting up the appliances in the home, not realizing each one of them is only going to be running a certain amount of an hour, and you're supposed to adjust that. So that this is a common mistake, and a fairly common way that people juice load calculation too. So something you guys were probably interested in. So those are the like really pretty simple low-hanging fruit stuff. Some of the harder things, and when I say harder things, it's either harder to be sure of, or just harder to know what's right. Like harder to find the information, or harder to verify that it's correct. So the biggest swag, and if you're not familiar with the term swag, it stands for scientific, wild, I don't know, we're going to keep it family friendly, guess. And so infiltration is the big swag here, especially on existing homes, but even in new construction a lot of times. I mean, I haven't built the home yet. So blower doors are for the win here. Blower doors are the most accurate way we have, right? Then I'm saying it's that way specifically on purpose, because they're not as accurate as people believe them to be in terms of determining real infiltration of a building. But they're the best tool we have for measuring it as of right now. And if you have access to that information, or the designer does, I would prefer to see that. ACH 50 number is what the code standard is written for. And so that's mostly what you're going to see, or the vast majority of what you're going to see. But there are these terms in Manual J for estimating the tightness of the building. And these numbers are specifically for a 2,600 two-story home in Houston, Texas. Okay. Those sorts of factors, right? The size of the home, the surface area of the home, the number of stories, the number of fireplaces, all these things can change these relationships. So these are not dead on nuts all the time in every location, but in the ballpark, a tight home is about 1.5 air changes per hour, which is very aggressively tight, right? That is bragging rights tight. A semi-tight home is still under 3 air changes per hour, which is currently the most aggressive standard that we have in the United States for building a house. Up north, we have to build the 3 air changes per hour because it's so much colder here. Average is around 4 ACH 50, which is, if you will note, slightly better than code minimum in Texas right now. I know there are a few locations that actually do use 4, but I believe the state is still on 5 for the current code cycle. And this is beyond that. This is tighter than a brand new house code minimum. Semi-loose is on the other side of that. Of course, it would be somewhere in between at 6 ACH 50, this is sort of my go-to for existing home. Nothing looks weird about it, right? And then loose is at 8 ACH 50, which is pretty darn leaky, but double-digit leakage rates are absolutely not unheard of. But they are problem homes, low-quality homes, extraordinarily old homes before we tried to seal them, that sort of thing. And what it looks like on the reports is it's just going to be an infiltration section. Again, the project summary, one of my go-to, this is a very good one to look at. Infiltration will either look like this for blower door, and it will say blower door, or simplified and give you that range. But it's good to know. Average is basically code minimum new construction, slightly better when calibrating what you see as average, tight, loose, and the in-betweens. So FYI, one of the things I look for when I see a load calc is when I have a house that's in this tightness range or above. This is a little bit of a coin flip for me, but if you're at semi-tight or tight, how should I have ventilation, right? The old school, like we used it for 20 years before we started getting aggressive, before 2010, we started getting aggressive about our ventilation standards. The old school rule was a third of an air change per hour natural. Okay. And natural air change rate's a 4 Pascal air change rate. That's not this number, right? It's a different number. This is the natural, this is the actual here. And you'll see that on the cooling column anyway, even average is below that 0.33 natural air change rate, meaning if you're semi-tight or tight, you should have ventilation, right? And if you're not putting ventilation in, I don't care if your code requires it or not. If you're not putting ventilation in, it should mean that the house is leakier than that, right? Because if you're saying we don't need ventilation, you're saying we're not building an ultra tight home. And it turns out semi-tight and tight are pretty freaking tight. They are aggressively well sealed by Texas standards. And like I said, average is sitting basically right on the line. I considered doing a cross out, but it didn't go all the way across the thing. So I would consider this line sort of right through the middle of average. That's a coin toss, right? Because that, by the old school standard, it's fine in the winter and not in the summer. That's something I look for. I look to find ventilation numbers when I see something that's semi-tight or tight, maybe average. That'll be up to you. Speaking of ventilation, which I will often jokingly call mechanical leakage because we use exhaust only ventilation from time to time. The problem with right soft, delete, cool calc, the whole lot of them is they aren't breaking down their ventilation calculations. They have all of them have like selectable Ashrae ventilation standards, and then they do the math and spit out the ventilation number, which is great. And we want to trust it. That's cool. You can check the inputs, right? The inputs for ventilation requirements are area, volume, and occupants or bedrooms. But if they're doing their internal loads correctly, the occupants should be the driving force because it will be the number of bedrooms +1 or higher. And so technically number of bedrooms could be part of that, but the occupant load is usually the driving factor. And if you wanted to see a breakdown of the math, you wanted to see it all laid out for you, my recommendation, you're probably aware of this site, but if you're not, it's called RedCalc, right? You can just Google RedCalc, you'll go right to it. Just a bunch of free building science tools. It is awesome. It is a building nerd's playground. And the online, so if you're not going to use it from an app or your phone, it's free to use those tools, and you can print there's a little print button on all of them, on the little calculators that you can have a printout from. The report itself will, this is what I would be looking at. I'd be looking at area and volume, right, to verify the information went in correctly. And that would generally give me a good idea as to whether or not the ventilation calculation was done correctly. That, by the way, is more HERS rater territory than plan reviewer territory, but I think we have both here. So then, of course, there's orientation. Very simple, but very important part of the load. There is I don't have a clock here. Okay, good. There is a little bit of a story behind this, but we're starting to fill up on time here, so I won't give you the long version of it. But an individual who worked at the ACCA at the time really wanted all the software companies to tell him where the front door was. And the software companies, more than one, tried to explain to him that that's not a thing that a computer knows, doesn't know what a front door is. And so it would become a manually input piece of information that would get tagged onto a report and would mean nothing, right? In any of the software programs out there, I can say the front door is wherever I want to say it, and it doesn't have an impact on the load because computers don't know what a front door is, man. And so I don't look for that front door orientation. I know for the purposes of having correct paperwork, you may need to see it and tell them to change. That's fine. But if you're looking to make sure if the load is correct, what you want to do is use the drawing if they have one, and multiple tools have those that print out. Or if they aren't using a drawing capable tool, then look for an identifying feature for the J1 form, right? So if I print the drawing, I'm going to get this little compass here, and that's pointing to north. That's the actual orientation of the building. That's the one that impacts the load and changes all the numbers and is super duper important. The front door is just a tag on so it could fill out the paperwork. So if I wanted to use the J1 form, if I didn't have a drawing, because they didn't use one, they're not required to. If I wanted to verify their reports, I would identify a simple feature, right? Here's a master bathroom. It's got one north outside wall, right? A room with one outside wall is a great way to do this. And if you look at your spreadsheet style printout, it's called the J1 form. That, again, all of the manufacturers of the software print out. This is why I like to use this for this presentation. I can find my master bath. I can find where the wall area is, and I can verify that it is in fact north, right? And so if I know I have a north facing wall there in my master bath, I know my orientation is correct the right way, right? The way that I can actually confirm the math got done. That front door thing became a red herring immediately. And it was just sort of a miscommunication on what software is capable of, or what it was capable of at the time. Okay, so the more difficult part of verifying information, and at a certain point, you have to ask yourself, how much is my job, making sure that somebody did every aspect of their job, properly. At what point are you redesigning the system? And that's not a line I want to draw for you, but it is a fair question. Building materials are obviously a huge factor that goes into a load calculation. And the ACCA is very big on its codes, right? They have these little 12C-OSW means R13 stud wall with no board insulation and standard siding, non-brick siding on the exterior. And you could try to memorize those and be one of the handful of people in the world that has made sense of that system. Or you could use the book as a reference guide, or you could just learn how U values work. It becomes really hard to pull one over on somebody as soon as they understand how the actual numbers work. It's a great way to cut through all the BS. So you can print lots of different reports from lots of different software, and a lot of it will be somewhat confusing because it relies on these code systems, and the code system itself is not as well structured as it should be. Between each type of building material, different places in the code do different things, right? There's not like one place for where the insulation goes. You would think there would be, but no. And so it can be hard to follow. It is systematic within each building component, but there's a lot of those because there's a whole bunch of different ones for walls and a couple of different ones for ceilings, and yeah, it can get a bunch of different ones for floors too. So like I said, learn how U values work. Real simple. You just flip the number, right? R values and U values are inverse or reciprocal of each other. So if I have the R value, right, which is, if you remember from high school math, R over 1 or R divided by 1 is still just R, right? 2 divided by 1 is 2. And so R over 1 equals 1 over U. All right. So you can flip that around and say, okay, well, I have the R value. I want the U value. Cool. Well, you take 1 divided by the R value, and that gives you the U value. I should have written those backwards. I apologize. So take that R value, take the number 1 divided by that number, and that's the U value. Except there's more than one R value in a surface usually, right? So it's never quite as simple as R13 is 1 divided by 13, because that would give you 0.77. That's supposed to have both of these are supposed to have a 0. Damn it. Sorry, guys. 0.077. Back. And 0.052, but the actual is 0.091 and 0.068. And this is because of something called thermal bridging, right? There's studs in between the insulation. So if the insulation is not in a uniform layer, and that affects output. And so you can understand the math here, but you're ballparking, right? You're not, it's not a precise R13 shall be 1 divided by 13, because your entire house isn't made of the blanket. It's got lots of studs and other things involved in the building process. But if you understand the basics of this, it becomes very hard to put in a bald face lie or a big quote unquote adjustment factor to tweak their load calculations if that's something they're trying to do. Please note, again, there should be a 0 there and a 0 there. I apologize. And so you could look at the J1 form and see codes, right? Just codes everywhere. In RightSoft, they have this thing called the component construction report. But what's important to me is that you can get really caught up in these descriptions, reading them. Man, so many of the variables that are in the dang book, like they have different codes for the materials. They don't calculate differently, right? Floors over crawl spaces, pier and beam, with insulation in the floor, with any insulation in the floor. Carpet and hardwood, tile and vinyl, they all calculate the same way, but there's different codes for them, and it'll show up in the description. And it'll look wrong, right? Oh no, this is hardwood and you have tile. Nope, that is not how that works. It's kind of confusing what some of the things have an impact on and what they don't. And so you can get really caught up in the minefield of these descriptions and, end up telling people to change stuff that literally doesn't change the load, which, by the way, probably puts your alarm bells off, right? They changed it, nothing happened to the numbers. Well, that's actually how it works. There are a lot of details that they include that could be important in a certain situation, but for consistency purpose, they put that descriptor on all of the materials. And when it didn't make a difference, it just duplicated the data. And when it did, it applied. But there's a few of them where there's only a handful of situations where it makes a difference. So instead of poring over this, I go right to my U value. Right? Not even this insulation port. I don't know how it is in Elite and Cool Calc and the rest, but we put this, or RightSoft put this descriptor in there for the purposes of, at the request of the same person who wanted the front door thing, wanted to know the essential R value. And so it is included here, but the real, this is just reporting stuff, right? This is not the actual value. The U value is the actual value. And that's where I find, that's where I can smell a rat. So if I was going to this level, which you might not be, it is pretty detailed to get to here. That would be the number I would sort of key in on, looking for something fishy. Let's see. Oh yeah. And then we got the really tough stuff. So the algorithm. Duct load. Duct load is a iterative multivariable formula for determining load and distribution. You can change a window on a building and the duct load will change, because that window was helping determine the rest of the load, which was determining the size of the system, which was determining CFM, which was determining surface area, which is what gets fed into the load calculation for duct load. Whew. So it's a snake eating its tail. It just keeps going around and around in circles, and it's pretty complicated. And so trying to parse it apart is extremely difficult. So what I would recommend is if you wanted, first of all, you make sure there is one, right? If you've got a house where the ductwork is in the attic, then we should see a number here, not a bunch of zeros. That's an easy one. If your ductwork, or if this number is very high and your ductwork doesn't seem like it should have a whole lot of load. So let's say you're using R8 and very well sealed duct. You're still going to get 20% plus in a lot of situations in a hot attic in Texas. Probably not too much higher than that for well insulated, well sealed duct system. And the weird thing is it can be a lot lower because the rest of the components of the building are putting the better insulated they are, the more downward pressure they have on the size of the system, which puts downward pressure on the surface area of the duct, which brings the duct load down. So the range it could be is really wide, unfortunately. But if I'm above, say, like the 30% mark, that's it's a reach, but in some of the hotter areas in South Texas, code minimum with a trunk and branch system might put you there. But the big things you're going to notice are if you've got a duct system in the crawl space and there's nothing in the attic and it's 20+% here, 0.20 and higher, that's a red flag. If the house is an encapsulated attic, spray foamed attic, there should be a duct load. Those aren't truly conditioned spaces until they start actively conditioning them and doing all the stuff they need to do to that. But you shouldn't be in the 20+% range, right? That's going to be low double digits to single digits in the percentage range. And so what you'd be looking for are those big discrepancies. Getting the fine-tuned, detailed information about duct load is like there isn't even a report for it. It's just such a tangled mess. I don't know if the other software companies have a similar report. Actually, a couple of them probably do because they don't use the advanced duct load model that I know Rightsoft uses and Elite uses. I can't vouch for the others. I'm not familiar enough with their products. So they might have a report for it, but for those that have the advanced stuff, it's really hard. So your best bet is to just focus on the percentages and look for something fishy. The next really difficult report. So that's the Manual J reports, right? Which was going to be the big thrust of this tutorial. But if I didn't mention equipment, I'd be doing a disservice because that's where the biggest disconnect in the inspection world happens, because we use AHRI, right? So step one, and there's a Spear tutorial on this that I gave, right? It's called "There's No Such Thing as a Ton," okay? Because there isn't, right? A ton is a unit of weight, and in the HVAC world, a ton is not a certain number of BTUs. Actually, it is. It's 286,000. Yeah, let that sink in for a second. We're not going to tear that apart because it'll take us all day. But it's not a real 12,000 is per ton is not a real thing, right? Even looking at AHRI data to tell me that, right? The problem is the only readily available to the general public clearinghouse of information is AHRI. So we want to use it, but we can't, guys. We cannot. Their data is not meant for sizing equipment. Okay. It does not have a split of sensible and latent performance. For crying out loud, can you like Houston, Texas, not knowing how much dehumidification an air conditioner can do? That's not right, right? And equipment at AHRI conditions is rated with a 95-degree outdoor temperature, which for a lot of Texas is pretty freaking close. Okay. And then an 80-degree indoor return air temperature. Constant. The whole test, 80-degree return air temperature. So it's as if the homeowner's keeping their home at 80 degrees with a 50% relative humidity, but at 80 degrees, meaning it's like a 4-degree increase in wet bulb, right? 3 to 4, actually. Both of which improve the performance of the system. So the second I put a system in Texas, it's performing worse than the AHRI ratings, okay? Because AHRI rated under these, in my opinion, stupid conditions, right? I agree with their outdoor, but the indoor ones, gosh. So in order to properly select a piece of equipment, you have to start with the manufacturer data. And it is built in, some of it, actually kind of a lot of it is built into RightSoft. A lot of manufacturers are participating in that, but not all of it, right? And new models are kind of slow to get the information in there. Elite has a tool for inputting the information, but is not getting it directly from manufacturers because it's a slog. It's not requires an entire person collecting a salary just to keep it up to date. And so that means for some, if not all, of the equipment sizing criteria, I have to go to the manufacturer's website to find that out, and they put it behind a paywall. You have to be not a paywall, but a password that you need to be a dealer to go look at. Add that to the fact that some manufacturers they don't publish very good performance data. Right? They might publish one condenser with one coil. That's it. Right? And just everything else is comparable, and they don't give you anything else. Right? There's not a bunch of them like that, but they're out there, and some of the bigger names too. And so getting the actual performance information is a hurdle at which you as plan reviewers and inspectors are going to stumble. It is a thing that some people that I work with or bump into a lot in the professional world have been trying to remedy and work on. And I'm going to end that at that because, well, when you talk about stuff like that, you reduce the chances it's going to work. But yeah, step one of sizing a piece of equipment is knowing how the thing will really perform in the real world conditions you're going to put that system in. And that's not something that you can easily verify. You could ask them to print the raw data from the manufacturer's site, but that would still often need to be what's called interpolated, meaning you'd have to take the weighted average of all these sort of data points. So this is sort of where there's going to need to be a little bit of trust. Finding that data is not an easy thing, right? Some manufacturers may publish it widely. Sometimes the distributors will post the basic ones, the basic charts on their websites that you can find. But as a designer, as somebody who designs HVAC systems, I sized a system the other day. The manufacturer didn't have the extended performance data for any of their new SEER 2 stuff. Nothing. So I had to go and look at I did comparables. I used a 14 SEER for the new performance for the new 13 SEER models and said a small prayer because the thing needed to be installed. And that's confirmed by the manufacturer. Sorry, we haven't published that yet. Like, great. And for what it's worth, contractors are just as frustrated about this as you are. Luckily for a lot of manufacturers, it is built into RightSoft at least, and they can hit a little magic button and it'll find equipment. Except when it doesn't, you may have to apply the spirit of the law, maybe not the letter of the law. I'm going to circle back to that point. First, I want to show you what a good manual S report looks like. What you can do is verify that sizing is within range. The rules are fairly straightforward. You always need to have enough latent capacity. That should be 100% or higher. You want to have enough sensible capacity, but it's okay if you're low. Right? It's okay if you're you're actually technically allowed to be under by 10%. I don't like to be under by that much, but that is the current limit. And the total capacity we want to, and both the sensible and the total, we want to be, sensible, total has the same rules as sensible. We want it to be between 90%, and I don't like being under on total at all, if I can avoid it. But I want to be between 90% and 115% for single stage equipment, 120% for two stage equipment, 130% for variable capacity equipment like inverter technology. Not always exactly inverter technology, similar to. Those are the magic 15, 20, 30. Those are the magic numbers that exist right now. And we want to do the best we can with this. If you are in a high humidity climate, that latent is the most important. Second most important by a very narrow margin is not having too much sensible, right? In an ultra dry climate, there is no good reason to undersize a piece of equipment, cooling equipment, because the negative consequences of being slightly oversized in that climate are negligible. And due to some of the vagaries of how equipment sizing works, it's harder to size equipment in high altitude climates. Adjustments in airflow do not affect the performance of the system as much as they do in humid climates, because it's not having an impact on latent load because it's near zero. So you will often find in dry climates that you're going to be getting reports that are showing numbers that exceed the limits, right? Over 115%. Well, there's a reason for that. And I believe that we need to be a little more aware of the spirit of the law versus the letter of the law. If you apply that limit, right, that 15% sizing limit, well, that means that if I am in this range here, right, where a 1.5 ton won't do the job, it's too small, but I'm not at least there, a 2 ton is technically too big, right? There is a huge range here. And these are drawn to scale for the record. There is a huge range here of what the differences are between the sizes at the smaller tonnages. I am of the opinion, like, we used to live in a 3-ton world, man. All right. Like, especially in Texas, people didn't even whole distributors didn't even stock 1.5 ton units in some places in Texas. Just nobody ever bought them. Right. It was all in this range. And those rules, they work great around here. Right. They work awesome. But down here, not so much. And so you must have enough latent. Extra latent is not a bad thing. There's no actual limit on latent. There's some language in there that says there is, but then the very next sentence says that there isn't. So it's very confusing part of the book. And speaking in terms of physics, there's really no such thing as too much latent. There is such thing as too much sensible, right? And there is such a thing as too much total, but not as much as being too much sensible, right? If I saw a system that was 2 ton and was 150% of my latent and 115% of my, or lower of sensible and slightly over on the total, that's a green light for me, because I know that the 1.5 ton would be too small, and that if I'm not accommodating, in my opinion, just the opinion of this one random guy here, but if I'm not somewhat accommodating to the realities of the field, I'm just teaching people to lie to me, right? I'm teaching people to find small ways to tweak my loads, and like, I'd rather not have them learn how to do that, right? Like, that is not information I want in their hands, and if I force them to do it, they'll get it. So this is a bit of an issue. It is an issue we're aware of. The next edition of the Manual S, if things continue on the way they have been, right? The loads under 24,000 BTUs are going to be allowed to be oversized by 20%. And then the 15% rule. So that the simplest, there's also going to be some more complicated methods for appropriately sizing a piece of equipment, but mostly having to do with heat pumps, and particularly in cold climates. So it won't be much of a thing in your area. But this is a change that so far has not, the code cycle is a process, but so far has not. We received an early challenge. We explained the math. The challenger was like, "Oh yeah, I guess you kind of have to," and here we are. So that is something, and it should be coming out late this year, early next year. So that is a change that's on the way. As for inspecting ductwork, personally, I just want to see the static pressure and equivalent length report. This would also have a friction rate on it, but seeing that they actually put in numbers to the static pressure tells me that they were using manual D. Trying to verify and inspect every component of a duct system is madness. I've worked with inspection teams in certain municipalities on ways to move away from it because it just was slowing them down, and they just switched to static pressure testing the unit once it was installed. Put the pressure on the onus on the contractor. Well, if it failed after the fact, they have to fix it, and more expensive to do that than do it right in the first place. So that ended up being a pretty effective approach. But if you want to ensure that they're using manual D, this is probably the easiest thing to read, that every manual D software is going to have too. They're going to have that available static pressure calculation and an effective length calculation. My last bit of advice is, so we did a whole chunk of what's in the weeds because, well, I'm guessing that's what everybody's not paying for here. What you were expecting to learn more about. But personally, I check a lot of load calculations for accuracy, not as an inspector, but just as a service to my customers. And the very first thing I look at is this. All of the software companies that do manual J's have these, and they're, with a little bit of common sense, a little bit of knowledge about the building, you can very quickly find the big mistakes, right? Or the big cheats, whatever it is, right? Looking at where the load is coming from component by component is one of the best ways. And just ask people to include it. And if you're not comfortable using it, you need to be more detailed at first because your brain doesn't have that macro perspective. That's cool. Take a minute to look at this or this type of report, because they're all, it's a pie chart, right? Wrights didn't invent the pie chart. They all got it. Take a look at this for every single one that you review, and then do your detailed review. And if you caught a mistake, make a note of that when you review this. But as you look at more and more plans, the human capacity for pattern recognition is off the charts. It's very, very good. If you look at a bunch of these, you are going to start to see patterns. And when something in the pattern is off, doesn't necessarily mean it's wrong, but it means there's something worth investigating. This is, I'm not advocating using this and only this for inspection, but it is, in my opinion, by far, like head and shoulders, the best step one to doing it. The problem is it's fuzzy, right? It's, I can't give you like, these are the numbers you shall see. Like, it depends on the scenario, but it's a great way to do some big picture thinking. And by the way, catch the biggest mistakes easily. Like the number of times I've looked at this and go, oh, here's your problem. Like without, when it looks like Pac-Man, yeah, something's wrong with that part of the building. It's a surprisingly simple tool and surprisingly effective. And the more you use it, the more you look at it, the better you get at it. Okay. I did not include a closing slide because I'm being perfectly honest. I was putting a few of these together right up to the wire. But that's everything. I do have some other materials. I can show you the websites I talked about, or some a breakdown of an actual report. If we want to go through it and you have specific questions on it, I can show you what you need. I've got the file open so I can generate one if it doesn't have what we need to talk about. But now would be a good time for some Q&A.
All right, well that's Alex, that was exactly what I was looking for on trying to help people with plan review. So I greatly appreciate all the information you put together. And I know we kind of did this in a rush, but this was the overview of what I was looking for. I don't have questions in the chat per se, but I do have a question with your thoughts on, and you spoke a little bit about it in the presentation, but your thoughts on actively conditioning encapsulated attics, which we're starting to see in Texas.
Sure. I think it's so better, smarter people than me have weighed in on this, but when I go to a building science, symposium, and Joe Steebrook is talking and tells me that, when you encapsulate a crawl space or an attic, you should have a transfer grill for return air to come out of it to remove that humidity, or enough penetrations in the envelope that it can, it says to me that, fire code wise, it's not that big a deal. And why don't we just condition the dang thing? Now I understand that code is code. I'm not, and you don't mess with the NFPA. I'm well aware of that from a job in a previous life. But I think it's an excellent strategy for maintaining comfort. There is potential for air quality issues if the attic is somewhat abandoned and critters decide to move in or something, but that's true of my basement too, right? So I'm very pro that. I think it's a very good approach, but I think a dehumidifier is an excellent substitute for it too, because it doesn't have to maintain the exact temperature of the rest of the house to be energy efficient. And really the only problem is moisture buildup in both the sealed crawl spaces and sealed attics. So yeah, if it were my home, I'd probably take the dehumidifier approach. I'm a cheapo. What's the best bang for my buck? And for me, that would be the dehu.
Yeah, I agree with that. And I guess the issue I was running into when I was doing energy inspections was the complaint and issue was sweating ductwork or raining ductwork. So instead of
Sure.
recalculating the load calculations, they just stubbed out a supply and stubbed out a return and said, you're good, which it solved the issue, but I think it clouded the load calculation
You
for the
see
rest of the house.
that's the thing though. But remember I was talking about humidity rises and your encapsulated attic is a moisture trap. It's not a guarantee that sweating ductwork or raining ductwork, as long as we're talking about the outside, which we would be if supply and return fixed it. That's not necessarily a load problem, right? It just means that the surface of the ducts in this very cool space, right? So those surface of those ducts, they're not in 130-degree air, keeping those surface of those ducts nice and warm, right? They are going to be cold, and that is normal. The air in there is 55 degrees, and the air in the attic isn't 130; it's like 80, right? So that's going to be a cold surface, and as soon as the dew point in the attic gets to that point or below, you're going to get sweat and rain. And so it does not necessarily. Could it be an oversized system? Sure, yeah. That could certainly contribute to it, because the higher levels of humidity in the house would mean higher levels of humidity in the attic. But since a good way to think about this is or a fun fact to know that can kind of help frame this mode of thought here. Heat cycles are, for the most part, we're not talking 12 inches of stone or something, typically daily, right? The walls heat up, cool off, heat up, cool off, heat up, cool off. And that happens on a 24-hour cycle. Humidity is much longer in the way it cycles through a home. Houses are more humid on the same conditions of the day, right? If the days are identical in terms of what temperature and what humidity they are outside, a home will be more humid in August than it will in June. And that's because all of the parts of your building are soaking up moisture over time, right? Your couch is absorbing moisture. Your rug is absorbing moisture. Your walls are absorbing moisture. Everything is, or everything that can is. And that cycle is behaving over a longer period of time, right? It's certainly not hourly, right? So it is very possible for a home with a properly sized HVAC system for humidity to build up. If air has a way to go, like seriously, a leaky bathroom vent is a big one, right? Those things are not really constructed very tight to begin with. And it is a great source of humidity entering the space with no way to remove it. And so it just builds and builds and builds and builds. So yeah, when I hear humidity in an encapsulated attic, the first thing I think of is not oversized system, actually. Humidity in the home, yeah, that's the first thing I think of. But in the attic, the encapsulated attic, nope, not at all.
That makes sense. That makes sense. Appreciate it. We do have
Yep.
one question that came from the chat. It said, what should specific pages or reports should a plan reviewer be requiring at a minimum from the software reports? Like you just named the building and
Yeah, so
analysis, and then
so
what
the
else?
pie chart, whatever pie chart they have, and the manual S report and the project summary report, I think would be the minimum. The manual S report is it's built so much on trust that you could argue that it is not as I'm going to look at it, I'm going to look at the numbers, and they're going to have come from something somebody typed in most cases that aren't RightSoft, or they're automated from the software. Really all you're verifying is those percentages. So that one maybe is just outside the minimum. But then something like a project summary, right? This is an actual copy of the report. If you are going to be more detailed, like if you're not going to dive into a greater degree of detail because you don't have the time, or it's not what you're supposed to be doing, that's fine. But if you wanted to dive deeper in, this J1 form is everything about the load is here somewhere, right? You just I just don't like using it for it because of things like this 12C-OBW. All right, that's a R13 wall with no board insulation and brick siding. Like, great. Like, learning how to read those stupid codes is really not my top priority. They're not great. I could use this for specific things to dive a little deeper, like my internal loads and my duct loads and things like this. So while I think the pie chart is a given for the minimum, a summary report, whatever they may call it, RightSoft calls it the project summary, would be like the bare minimum. Next, I would say the J1 form and the manual S report. After that, you don't really need much unless you're doing duct verification. And if they're doing duct design, I'd probably ask them to print the drawing. This one didn't have a duct design, so I wasn't able to show it. I didn't realize that until I left the duct design stuff for the end, and didn't realize until way too late. But yeah, that's bare minimum pie chart and summary report. Next level, manual S and J1.
That works. And then Bill also asked, he says, I noticed many times that the energy code reports are not completed properly. How can a plan reviewer ensure the person filling out the report / software is qualified to do so? And then does the software companies require their users to first be qualified in some way or certified? If not, maybe they should.
Well, I wouldn't go putting that one on the software companies. Their goal is to sell software. If you tell them they have to certify people to sell software, their goal will be to certify people. And certifications are often become a very BS kind of process. Go get certified as a HERS rater. Tell me how much you trust certifications. I'm certified as a HERS rater. I watch the instructor tell people, you got this many wrong. I wouldn't put it there. But again, not to let cats out of bags, because that tends to slow progress. I've made that mistake before. I'm trying to learn my lesson there, but I will say that I am working with a national organization on a certification program. I would be more directly involved with it, but I asked them, would I be allowed to write the test and teach the class? And they said no. So I turned down the job and found them somebody else, and am helping in any way they can. It is my goal to eventually be teaching people and certifying them, but there is currently no certification process. Now, ResNet, I think it's ResNet, I believe ResNet just created a credential for doing the computer side of the energy calculations. But the last I checked, so there is a division between energy and HVAC, and I am much more in the HVAC world. I touch on the energy world in a lot of places, so I keep abreast, but it's not my bread and butter. So take this with a gigantic grain of salt. But last I checked, that credential is not particularly well defined and does not have, like, I don't think you can sign up for a class or a test yet. But they've created they've started the process as well, a certification process for the guy running the computer, not just the guy in the field. So that is a thing. Whether, you know, how it looks and how it works, I don't think that's been well ironed out yet.
That makes sense. And yeah, ResNet's really good at doing that. You know, they split the RFI and HERS raters. So a HERS rater can do energy reports and energy modeling, but an RFI, which is just for field inspections only, can run equipment but can't do the energy calculations or energy modeling. So they've started splitting those certificates.
Well, and I believe they have a modeling. I believe they have a modeling only.
Now they have a modeling,
or they're working on a modeling only.
Right, and that's what they're working on. And a lot of it becomes and stems from those kind of things. But Bill, to answer part of your question too, is the code is kind of vague, and it does say that the code official has the right to approve or not approve software. It doesn't specifically state that that person using that software has to be certified in any way. It's just the software that's being used has to be approved.
And there is a certification process for the software.
Right.
ACCA certified. They keep a list on their website. The ACCA does, of what's certified currently for Manual J, Manual S, Manual D, etc.
Yeah. And that's usually what a CBO or a building official would look at on ACCA's website to say what's approved software. And then if there's anything else turned in, it's not approved by the city and it's not being used. But to know whether or not the person using the software is certified, they could be under one person's license and have 12 other people at the office, but all of them are working under one license. That happens from time to time, doesn't mean that they've been fully qualified. So that's tough to differentiate kind of who is running that software and it's actually been fully trained.
Yeah.
So, all right, well, it's right up at 1 o'clock. I really appreciate it, Alex. Thank you so much. This will be uploaded to YouTube.
Cool.
Not long after this, probably in a couple of days, it'll be up on YouTube. You guys can be watching if you have any questions. Always reach out to me if you have any questions at all. I will, if I'll take control, I'll share my screen real fast. If you want to stop sharing, then I'll just share the last two slides that I have.
Yep, and I have to, come on, how do I stop sharing? Come on. There.
Should be at the
bottom. No, I moved the bar.
Yeah, I do that too. And then just, I appreciate, I know you stay busy. Thank you for putting this together for us to do this. I know you're extremely busy all the time with what you do.
Yeah, I got to dip out in the next 60 seconds actually. So thank you very much for the opportunity.
You're welcome to go ahead. I appreciate it, Alex. Thank you so much.
You're quite welcome. Thank you.
You bet. Appreciate it. All right, guys. So you should be able to see the screen that I'm sharing now, which is the next webinar that's coming up. It's code requirements for HVAC. It's a rerun that was presented by Brett Dillon from the Dillon Group. He's basically titled that we've been doing this for 39 years. And so he kind of goes into a deep dive. It's an hour and a half long. There's a deep dive with kind of, this is the way we've always been doing it, but it doesn't mean that it's right. So that's going to come up on the July 20th. I've got a lot of in-person stuff that's happening, so we're not having a whole lot of webinars. I will get back to that probably in August and September and do a bigger push for that because our contracts will end in September. And then, of course, my contact information here, if you guys want to screenshot that or take a picture of that, take note of it. Always reach out to me if you have any questions. And again, thanks for your time today, and everyone have a great and safe holiday, and we'll talk to everyone on the next video. I appreciate it, guys. Thank you.